dear learners, in our earlier lectures, we have learned many aspects about the Earth's ionosphere, the structure of ionosphere, the photochemistry of ionosphere, the variability of ionosphere, all that, right. So, what we have built upon so far, we have seen what is ionosphere. I believe all of us are now very familiar with the basics of ionosphere. So, what is ionosphere? We have seen what is the variability of ionosphere. So, when I am talking about the variability, I am always referring to the variation of electron density versus many things, versus height, versus season, versus latitude, versus solar cycle, etc., etc. And what are the layers of ionosphere? Different layers, and what are the aspects related to photochemistry of ionosphere. So, we have seen all these things, right. Now, when we talk about the layers of ionosphere, we have a simple variation, something like this, where you define the D layer, E layer, F1 and F2 layers. Now, the question is why the ionosphere or the density of electrons in the ionosphere change with respect to height in this particular fashion. So, this is the electron density and this is the height. So, it is reaching a maximum value and thereafter it is decreasing, and then again for small variations it is reaching a maximum value. So, there are some distinct peaks, very distinct peaks, and but there are no distinct peak in the D layer, right. Now, in order to understand this, or in order to have a mathematical formalism to derive, I mean which can reproduce this variability, we need a theory, we need an analytical theory. Okay. Such a particular theory was proposed by Sydney Chapman, okay, Chapman's theory. Okay. Chapman's theory gave an idealized height distribution of ionization as a function of altitudes, which is produced solely by the absorption of solar radiation. It gave a idealized height distribution of electron density with respect to height. This is the distribution that I am talking about. So, this distribution mathematically was given by this Chapman's theory. So, we will now, what we will do is, in this class and in the next class probably, we will look at various assumptions that the Chapman's theory begins with, and we will derive the production rate of electrons with respect to height. In the process, we will try to understand what are the variables which are relevant for deriving the height distribution of electron density. Okay. So, Chapman derived the shape of such a layer mathematically. Chapman's theory is the mathematical treatment of deriving height distribution of electron density in the ionosphere. Okay. Now, the basic idea is very simple. The solar radiation in terms of XUV or X or anything ionizes the atoms and molecules, producing the ions and electrons, right. So, now we talk about production rate. What is rate? The number of electrons produced per unit time, okay, and we call it as the production rate. So, we define production rate as Q. So, the rate at which electrons are produced at any altitude is proportional to the density of species. Do you agree? How many electrons can be produced? As many number of neutral atoms are there, they can be ionized and electrons can be produced. So, Q will be proportional to the number density, let us say capital N, number of neutral species which are present. And it is also proportional to the intensity of electromagnetic radiation that is available at that altitude. So, Q should also be proportional to the intensity of electromagnetic radiation. So, let us say if there are 100 photons and if there are 100 atoms, you can produce more number of electrons if there are more photons, and if there are more photons, but there are not many number of neutral species which can be ionized, then obviously the total number of electrons produced will be dependent on the number of neutral species which are available. Okay. Exactly opposite. If you have more number of atoms and if you have less number of photons which can ionize, then the total number of electrons produced will be dependent on the number of photons which are available, right? So Q is proportional to the cross section, like absorption cross section, how effectively a photon can be absorbed by an atom, leading towards the ionization, right? Now, at the top of the atmosphere, let's say you're talking about the beginning of atmosphere. Okay, let's say the beginning of atmosphere, the electromagnetic radiation is coming like this. At the top of the atmosphere, the rate is very small as there are less number of atoms, more number of photons. Like I said, you have these two numbers, let's say number 1 and number 2. And if these two numbers are equal, of course, the number of electrons produced will be equal to one of these numbers because they are themselves are equal, right? Now, if this n1 is very, very small in comparison to n2, then the number of electrons will be equal to the n1, okay? And if n2 is very, very small in comparison to n1, let us assume that n2 to be the number density of neutral molecules, neutral atoms or neutral molecules, and this is the number of photons, okay? So, whichever is larger will not decide the electron density, whichever is smaller will decide the electron density. So, at the top of the ionosphere or at the top of the atmosphere, where the electromagnetic radiation starts to penetrate or starts to move inwards, the number of neutral species is very, very small. Despite the fact that there is more electromagnetic radiation availability, the number of electrons produced will be small. So, as this radiation is traveling towards the lower atmosphere, okay, it is traveling into an optically thick medium. So, what happens? The intensity of this electromagnetic radiation, I is equals to I naught e to the power of minus mu x. X is the distance, I naught is the initial intensity, I is the intensity at any given point. Okay. So, if you are defining this to be your x, or this distance is what you have traveled. So, at the end of it, at the end of traveling this x distance, the intensity if you measure, and if you know the intensity to begin with as I naught, this intensity will be exponential minus times the original intensity, which is of course going to be very, very small. Right. Now, but what is happening in this process is very, very important. What is happening is, as this radiation is traveling towards the surface, it is encountering more and more number of atoms. Do you agree? More and more number of neutral species which can be ionized. But at the same time, the available intensity as it is traveling towards is becoming smaller. So, there is larger availability of atoms, but the number of photons which can ionize is becoming increasingly smaller, right? So, you have an exponential decay from the top towards the ground, right, e to the power of minus mu x. This is decreasing like this, and you have an exponential decay from this bottom towards the top. You have two opposite things. So, if you go back to this number of n1 and n2, you assume n1 to be the number of photons which are available for ionizing and n2 to be the number of neutral atoms or molecules which can be ionized, then sometimes at the top n1 is very, very large than n2, then who will decide? The total electron density available will be decided by n2. And when you go towards the bottom, n1 becomes very, very small in comparison to n2. As a result, who will decide the number of electrons? Which will be n1. So, both the places you have very small numbers. So, you have to have something, a distribution which is something like this, because here also the number of electrons will be small, and here also the number of electrons will be small. But somewhere in between, you can expect that there are ideally equal number of atoms. So, you have n1 is equals to n2. So, what happens now? Which is effectively, which will be very, very large, because all the available photons are contributing towards the ionization, making the electron density reach a maximum value, right. So, this is the basic idea, right. So, competition between neutral densities and intensity will decide the ionospheric layer or the formation of the ionospheric layer. So, at the top of the atmosphere, the rate is very, very small, and as there are less number of atoms and molecules available for ionization to happen. So, as the radiation travels into the atmosphere, the concentration increases, so does the production rate. Okay, so we have already defined the production rate to be proportional to the intensity, to be proportional to the number density, and to be proportional to the cross section. Cross section, what is cross section doing? Cross section defines the statistical probability of a photon getting absorbed by an atom. Okay. So now Q is not a constant. Q depends on all these things, right? So all these intensity, number density, cross section, their variability will influence the production rate. Which means if you see how intensity is changing, let's say I'll write I is equals to I naught e to the power of minus mu x. Okay. And if you talk about the number density, and if you're coming from the top towards the surface, the number density has to be n is equals to n naught e to the power of, let's say, h by h, not minus but plus. What is sigma? Sigma can be a summation of sigma 1 plus sigma 2 plus sigma 3, etc. What are these sigma 1, sigma 2, and sigma 3? We are defining the absorption cross section for a particular species. So, the species, let's say if it is oxygen, nitric oxide, nitrogen, etc., different species have different absorption cross sections. This is basically an effective area over which this absorption can happen, and depending on the size of the molecular atom, the absorption cross section changes. So effectively we can combine these things, and we can say that this is the effective absorption cross section of the ionosphere, right? Now this also changes as you go across the altitudes. This also changes at different altitudes. The concentration or the major neutral species will change, we know that very well, and depending on that, the absorption cross section also changes. So all these parameters will effectively dictate variability in the production rate. So production rate has to be minimum at some point of time, and has to be maximum at some point of time, and it has to be minimum again, right? It should also, the most important variability that has been forced onto Q is the exponential decay of intensity and exponential growth of number density as you travel from the top towards the bottom. Okay. So, the peak production is reached when the intensity is just enough to ionize atoms and molecules as it travels further down. The number of atoms will increase, but due to the low availability of photons, the production rate further decreases. This is simple. I mean, this is what we know very well, right? We've already defined in our characterization or classification of various layers. We have defined what is called as the H max or HM, and then we have defined what is N max or NM. HM is the height at which NM appears, and what is NM? NM is the peak electron density. So, the height at which maximum production rate can happen can be understood from a simple argument of exponential decay from either sides, right? Now, for simplicity in this mathematical treatment, what we will do is we will assume the atmosphere or the ionosphere to be made up of a single species. We don't have to worry about this summation of sigma 1, sigma 2, sigma 3. That means we are not allowing variability in terms of the variety of neutral species which can be present. So, the height at which maximum production can happen, of course, can depend on this. Suppose the atmosphere consists of a single molecule, all of them having same absorption cross section, single species, right? So, single species, which means we have a single sigma, right? To be able to accommodate a general scenario, we can assume the radiation is traveling in an oblique direction. Okay, radiation is falling onto the surface at an oblique incidence, right? So, this is the surface of the earth, this is the normal, okay, this is at 90 degrees. Okay, now radiation is falling onto this, radiation is falling in an oblique direction. So, this is the intensity. So, this oblique incidence, as it travels down this column, the intensity will decrease, right? So, let us we draw a unit cross section in the direction of incidence. So, we imagine the sun to be here, and we imagine the radiation traveling through a unit cross section drawn in the direction of incidence, and the length is sufficient to contain n number of atoms or molecules. Now, in this case, let us say we restrict ourselves to the single species atoms. Okay, so we have this column, and within this column there are n number of atoms present. Okay, and all these atoms are identical. So, the absorption cross section of all these species is the same. Okay. So, if there are n atoms all with the same absorption cross section, the total projected absorption cross section becomes n sigma. the total projected absorption cross section simply becomes n sigma. And by simple argument, we can say that there are n number of atoms and there is cross section area which is available for the photon to get absorbed is sigma, then n sigma becomes the total absorption cross section that has been offered to this incident radiation at oblique incidence. Let us say we define this angle also as chi. We will come back to what is chi. Okay. Now, we can consider when n sigma becomes equal to 1 by simple argument, the entire radiation is absorbed. Whatever the radiation that is coming into the radiation is completely absorbed. That's it. So, the height at which maximum or complete absorption has happened can be defined by using the same condition as when n is equals to sigma inverse. Wherever n becomes equal to sigma inverse, that height becomes the height of maximum absorption or height of peak production. So, the rate of production can be dependent on this, right. Now, let us define what is called as production layer. What is a production layer? Production layer is a plot in which we have production versus height. We have production versus height. This is called as the, before we introduce the assumptions of the Chapman's theory, we will just look at the basic things that we have learned about the Chapman's theory or the ionospheric layer is that the production rate, the rate at which electrons are produced per unit time is not constant throughout the ionosphere, or for example, the electron density is not constant. So, what decides? It is just a competition between the number of photons available and the number of neutral atoms which are available for ionization, right. So, effectively starting from the top of the ionosphere, moving towards the surface, we realize that it is always an interplay between these two things. One, intensity is decreasing, same story again and again, right. Now, in order to combine this, we made a simple assumption that radiation is falling onto the surface in an oblique direction and a unit cross section is offered for the radiation to travel along, and within this there are capital N number of atoms, all of them having the same cross sectional area. So, that means when n sigma becomes equal to 1, we can consider the radiation to be completely absorbed. And if you want to define the height at which this radiation becomes completely absorbed, we say that whenever the number density becomes equal to the inverse of the cross section, we say that at that height the radiation is absorbed completely. Okay. So, we will continue this discussion by discussing the assumptions of Chapman's theory, and subsequently we will see how we can mathematically formalize the Chapman's theory. Yeah. So, with this basic understanding, we can summarize our objective into simple points, let us say. So, the shape of production layer, what is production layer? Production layer is rate of production versus height. So, the shape of production layer depends on the atmospheric species and as well as the incident solar radiation. Number 1, we have to assume that the radiation changes with respect to altitude, the radiation or the intensity of radiation changes with respect to the altitude, and the density of atmospheric species which is offered to the radiation for the sake of ionization also changes with respect to the altitude, and the absorption cross section will also change, but we can keep it as absorption cross section changes for different species. So, as in we can keep this as a constant, and more importantly the radiation will be absorbed, radiation which is incident in an oblique incidence will be completely absorbed at a particular height where the number density is equal to or is equals to sigma inverse, right. So, this is our condition, right. So, in Chapman's theory, what we are going to do is we are going to obtain the mathematical treatment for a production layer for few basic assumptions. This mathematical treatment is going to be valid for a production layer for oblique incidence, oblique incidence. Number 2, for an atmosphere which is horizontally stratified, horizontally stratified. What does it mean? It means that the atmosphere is homogeneous at any given altitude. Let us say you take 10 kilometers, wherever you go at any given latitude, the concentration of the atmosphere or the pressure of the atmosphere is constant. So, there is horizontal stratification. Okay. So, there are no gradients in the atmospheric density in the horizontal direction. And number 3, the Chapman layer or the production layer for an atmosphere with the scale height maintained as constant. The scale height is constant. You know what is scale height, right? And distributed accordingly in the atmosphere. And most importantly, this Chapman layer or this production layer is valid for an absorption cross section sigma, which is independent of incident lambda. Okay. So, such a layer which is the production layer which is valid as per these 4 assumption is called as a Chapman's layer. Okay. So, Chapman's theory produces or provides the rate of production as a function of altitude and solar zenith angle for an atmosphere which is defined in terms of conditions 1, 2, 3 and 4. So, Chapman's theory provides the rate of production Q for an atmosphere which is obeying these 4 conditions as a function of altitude, let us say, which is h, and solar zenith angle chi. This is the basic objective of the Chapman's theory of layer production. So, right. So, what is solar zenith angle? Solar zenith angle is the angle at which solar radiation is incident into the Earth's atmosphere. So, this is the normal direction. If you consider this to be the position of the sun, okay, this is sun. So, the radiation at this point is falling at this angle. So, this angle is chi, or this is also called as the solar zenith angle, usually denoted with chi. Let us say sunrise is here and this is 90 degrees and this is the sunset. Okay. So, at the same time of sunrise it is 0, 180 sunset, and exactly in the afternoon the solar zenith angle will be 90 degrees, right. So, this is the basic idea of Chapman's theory. So, why do we need Chapman's theory? Chapman's theory provides us a simple mathematical treatment for the rate of production, which is also called as production rate Q versus height and solar zenith angle. Is the Chapman's theory always valid for any atmosphere? You ask, no, it is not. We assume that the radiation is incident in an oblique direction, and we are considering the atmosphere to be horizontally stratified and the scale height is constant. So, scale height being constant, capital H is equals to kT by mg, right, capital H is equals to kBT by mg. Okay. So, if you want the scale height to be constant, you have to have temperature also to be constant, and gravitational pull within the shorter distances, the gravity will not change much, and capital M of course changes as you are moving towards a diffused state of atmosphere. The mean molecular weight will change because the percentage of molecules, a certain number of molecules to be present in equal ratio becomes less possible, right. So, despite of all this, we assume the atmosphere to be horizontally stratified and distributed vertically with a constant scale height, and the absorption cross section sigma is independent of the wavelength, right. So, that is the Chapman's theory or the basic purpose of the Chapman discussion about the Chapman's theory, right. So, we will continue with the mathematical treatment and basic assumptions of Chapman's theory in the next lecture.